Contents lists available at Science Direct, Internet of Things, Journal homepage, www.elsevier.com/locate/IoT. Measuring the impact of post-quantum cryptography in industrial IoT scenarios. Sus Cruz-Piris, A, Andrés Marín-López, B, Manuel Álvarez-Campana, B, Mario Sanz, B, José Ignacio Moreno, B, David Arroyo, C. Universidad de Alcalá, Departamento de Automática, Escuela Politécnica Superior, Campus Universitario, 28871, Alcalá de Henares, Madrid, Spain. Departamento de Ingeniería de Sistemas Telemáticos, ETSI Telecomunicación, Universidad Politécnica de Madrid, Avda Complutense, 8040, Madrid, Spain. Instituto de Tecnologías Físicas y de la Información, Consejo Superior de Investigaciones Científicas, Serrano 144, 28006, Madrid, Spain. ATICLE-INFO. Link to https://doi/10.5281/zenodo.14058. Words: quantum threat, quantum computing, networks and applications security, security, TLS. ABSTRACT. The continuously evolving nature of cryptography is driven by the emergence of new threats and attack vectors. Quantum computers pose a paradigmatic security risk to cryptography, challenging its very core principles. This quantum threat can be appropriately addressed through quantum-safe cryptographic primitives, such as quantum key distribution and post-quantum cryptography, PQC. In the case of PQC, the paradigm shift involves using algorithms with significantly higher computational costs. This paper analyzes the possibilities and challenges transitioning from current cryptographic systems to PQC alternatives, with a focus on the critical case of constrained resource devices. We demonstrate the feasibility of such a transition in IoT and IIoT scenarios with limited nodes, and we evaluate how new proposals mitigate the impact of signature computations on securing IoT/IIoT devices. In this work, we design and implement a novel framework to conduct an extensive set of experiments measuring the performance of different families of PQC algorithms in terms of execution time and power consumption. Both the framework and the dataset have been published in the EU Open Research Repository Zenodo to facilitate the future selection of algorithms that best adapt to the specific characteristics of each system. Introduction. Quantum computing promises new advances in parallelism beyond the capabilities of classical computers. Such advances can only come from two characteristics of quantum physics: superposition and entanglement. Qubits exhibit the superposition of different states, which represent the non-determinism of the physics of elementary particles. Only when we directly observe them will a particular state be observed. The qubits are represented as the superpositions of different states that can be observed, where each state is characterized by an amplitude. Amplitudes are complex numbers of the form A plus BI with A, B in R. The square of the modulus of the amplitude of a state represents the actual probability that the state. This article is part of a special issue titled Post-Quantum IoT Security, published in Internet of Things. Corresponding author. Email addresses louis.cruz@uha.es, andres.mop@upm.es, Manuel.Álvarez-Campana at upm.es, Mario.Sanz@upm.es, José Ignacio Moreno at upm.es, David.Arroyo@csic.es, IET:/SSDS:/NICT/IOT/LISIOT, IoT:/SSDS:/NICT/IoT/LIIOT, ABSTRACT:/FOA:/FOA:/FOA. Introduction. Quantum computing promises new advances in parallelism beyond the capabilities of classical computers. Such advances can only come from two characteristics of quantum physics: superposition and entanglement. Qubits exhibit the superposition of different states, which represent the non-determinism of the physics of elementary particles. Only when we directly observe them will a particular state be observed. The qubits are represented as the superpositions of different states that can be observed, where each state is characterized by an amplitude. Amplitudes are complex numbers of the form a plus bi with a, b in R. The square of the modulus of the amplitude of a state represents the actual probability that the state Cruz-Piris et al. Erved. This introduces a limitation in the amplitudes, since the probability that each state is observed is between 0 and 1. Sum of all potential probabilities must exactly equal to 1. Entanglement is a key feature of quantum mechanics. It is primarily relevant to quantum cryptography, particularly quantum distribution, QKD, but does not directly affect post-quantum cryptography, PQC. Extensive research activity has been performed on quantum-resistant algorithms. Though there is no general agreement on terminology, it is commonly known as post-quantum cryptography, PQC. PQC includes different algorithms based on mathematical problems, which are also exponential in complexity with the key size. PQC's main characteristic is that quantum computers are known to have advantages over classical computers in solving such problems. Besides enhancing confidentiality, PQC also improves crypto agility, as it increases the number of usable cryptographic systems, thus the opportunities to switch to a different system if the current one is suspected to be vulnerable. In the context of agility, quantum key distribution, QKD, have also attracted significant attention. QKD enables the quantum-safe distribution of symmetric keys using two channels, one quantum channel, typically a physical medium that exploits the quantum feature of particles, usually photons, and a secure classical or post-quantum authenticated channel. Some protocols allow recovery of the key sent over the quantum channel using additional information transmitted through the classical channel. In one, PQC and QKD are evaluated as part of their privacy-preserving approach. In this work, we propose a framework for characterizing the behavior of IoT devices using new post-quantum cryptography algorithms. We focus on validating the correct operation of a selected set of PQC algorithms for key generation, digitin, and other fundamental tasks, particularly in terms of their energy consumption. Additionally, leveraging the latest implementations, we simulate the operation of a certification authority, CA, application, one of the most common tools used by IoT devices for secure communications. Our evaluation considers both computational feasibility and energy efficiency, assessing the viability of native PQC integration in IoT environments. Section 3 details the experimental setup, devices used, tests performed, and our custom energy measurement system. Due to the volume of data, all numerical results are stored in a public data repository, too, which also contains the test framework for reproducibility. Summary results and insights are discussed in Section 4, followed by conclusions in Section 4.5. Related work. In recent years, major institutions such as the European Telecommunication Standards Institute, ETSI, the U.S. NIST, the Internet Engineering Task Force, IETF, and the International Organization for Standardization, ISO, have promoted initiatives to the development and advancement of cryptographic algorithms that are secure in the post-quantum era. The NIST contest for standardizing the new post-quantum CHEM and DSA algorithms, defined in August 2023, the first PQ standard algorithm derived from Crystal's Kyber, ML-Chem FIPS 203, with 3 parameter sets, 512, 68, and 102, according to the security levels defined by NIST. It also defined a new digital signing derived from Crystal's dilithium, MLDSA FIPS 204, and the third one derived from Sphinx Plus, SLHDSA FIPS 205, and a third DSA standard based in Falcon, still in draft status, NSIT 26. There has been a fourth call asking for new signing candidate algorithms, and by the time this article is being written, those are in the round 2 to collect public comments for the new candidates. Note that the scenario is still unclear, since some of the algorithms that are being proposed now have not received sufficient attention from the cryptographers community. For instance, known shortest vector problem, SVP, over lattices has been recently solved for 200 dimensions in less than 45 days, c. Key encapsulation mechanisms allows the derivation of a symmetric key from a public key scheme. Every CHEM implement with 3 entries. Key generation, sec param, equals PK, SK, to produce a pair public secret key, PK, SK. Endcaps, PK, equals SE, CT, which takes the public key as input and produces a symmetric key of 32 bytes, SE, and a cipher, CT. Decaps, SK, CT, equals SE, which takes as input the ciphertext and the secret key and produces the identical symmetric key as previous step, SE. Public keys are sent to the other party or known in advance by the other party, as in 8. Ciphertexts are sent the other way around, that both parties in a common symmetric key, SE. In the latest status report from the NIST, 9, only HQC has been selected for standardization. BIKE is not selected because there is not enough trust in the security underlying, as in HQC. Classic McLeese is not selected due to the huge size of the public key. They are open to standardization if another widely used standard appears where public key are pre-distributed and very small. Ciphertexts are favored. Since the first round of the NIST contest to select alternatives to CHEM and DSA based on exponentiation and discrete logarithm, Internet of Things 34, 2025, 10. Cruz-Piris et al., Digital Signature. Among the digital signature studies, 10 considers implementations of PQC digital signatures dated from 2022-2023. 11 article integrates several results from studies 19 to 24 regarding execution times or computing cycles in different architectures, e.g. generation and digital signature generation and verification. The paper draws the following conclusions about 1. Convenience of using Falcon in those systems where public keys transmission and digital signature verification is more often. 2. Dilithium advantages in low-power scenarios. And 3. Sphinx Plus robust security, the cost of computational efficiency. These results underscore the importance of context-specific deployments in specific source-constrained technological applications, as IoT and smart cards. Possibly due to the proved robustness of the security functions, there are several improvements proposed for Sphinx Plus, such as compressing, 25, using Korean block CYP, AEM and LEA as internal hash functions, 26, or using Haraka v2 hashes as in 24. Finally, on the application to the market, 27, focuses on implementing the PQC signature schemes inside a popular open-source Android email application add-in and comparing their performances to RSA 4096. It is no surprise that the results show overall dilithium faster key generation, verification, and with a relatively affordable key and signature size. Ravi et al. In 28 compares the security and the performances of the finalist post-quantum ciphers of dilithium, Falcon, and Rainbow. The authors compare the algorithm's computational loads in the execution time as well as the communication costs, implementation overheads when integrated with TLS and TCP/IP. The results show that dilithium-2 is the quickest for signing messages shorter than 390 kilobytes and Rainbow IA Classic for signing messages longer than 390 kilobytes. Dilithium-2 is quickest for verifying messages shorter than 460 kilobytes and Rainbow IA Classic for verifying messages longer than 460 kilobytes. When the algorithm is integrated for signing messages in TLS, dilithium-2 is the best both in connection handshake time and in processing, while Falcon 512 has the shortest certificate size affecting the payload and memory size. For networking-constrained applications, dilithium-2 can also be chosen in order to minimize the number of transmitted packets. But if the PQC DSA is used in TLS, then Falcon 512 would be a better choice. Chem. Paquet et al. In 29 developed a framework github.com/xvzcf/pqtls benchmark to evaluate different KEM schemes, fracas, features in TLS 1.3, analyzing the impact of different network losses. They restricted the study to 3 PQ, Frodo 640, Kyber 51290, Psych, and 1 classic algorithm, NIST Prime 256 or P256. The conclusions were that only for short RTTs the computation time of the KEM is noticeable, and also that packet losses above 20%, the number of packets required to transfer the public key or the ciphertext of the KEM, strongly penalized Frodo. This work was recently extended by Henrich et al. In 30 to analyze TLS handshake performance under variation of network parameters such as packet loss to investigate the suitability of PQC-KEM in specific application contexts. The research agrees with Paquin that handshake duration increases with poor network connectivity, and the data-intensive PQC schemes are more affected. According to 30, Kyber and other structured lattice-based algorithms achieve good overall performance and partially beat classical schemes. Other approaches such as FrodoChem, HQ, and Bike suffer individual disadvantages. For those algorithms, there is a clear performance decrease when increasing the security level or using a hybrid implementation, a combination with ECDH. The article concludes that performance is strongly influenced by the underlying network process, which must be considered when selecting PQC algorithms. IIoT scenarios. As is common in the development of cryptographic systems, numerous studies focus on validating new proposals, particularly emphasizing their performance measured by the execution cycles required to complete the entire process. 3. The literature also provides extensive analysis of the challenges this technology must overcome, outlining the potential attacks it needs to withstand and in scenarios in which it may encounter greater difficulties. 31. Analyzing this topic in environments such as the Industrial Internet of Things, IIoT, is particularly interesting due to the specific characteristics of its devices. IIoT refers to IoT networks in an industrial environment and are prime targets for cyber attacks. Current IIoT networks today use classical cryptography for protection and must also be protected against the transition to quantum computing. IoT is a domain that faces various challenges in architecture design, routing, and security issues of routing protocols. the type and number of devices that make up IoT networks, power consumption is a limiting factor in the search for solutions to these challenges. Whether it is the search for distributed computing paradigms, 3435, wireless networks, 3638, or secure Cruz-Piris et al. Experimental setup. The experiments carried out in this work aim to study the feasibility of integrating post-quantum cryptography algorithms in IoT environments. We have developed a framework to make it easier the definition and execution of the experiments. Frameworkers is instrumented in scripts that have a first part where the different algorithms under test are selected and the number of repetitions is defined. There are different scripts including the tests of chem agreements in TLS handshakes. Algorithm selection has been carried out considering the underlying mathematical problems and the size of the keys used. These two factors will enable to test the devices and characterize their performance in terms of execution time and energy consumption. We have selected devices based on ARM processors, widely used in these scenarios, with 32-bit and 64-bit architecture. Furthermore, we have set a set of tests focused on key encapsulation mechanisms, certificate generation, and digital signatures using classical and post-quantum algorithms. We measured the partial and total execution time and the energy consumption required by each device to complete the task. These results allow us to evaluate the feasibility of the PQ algorithms in this type of scenario. IoT devices and energy consumption monitor. Compared to conventional workstations or servers, IoT devices are often limited in terms of performance and memory size. To evaluate the PQC algorithms, we have selected 3 popular devices with different ARM processor generations and performance. We'll also perform the same tests on a conventional server since most state-of-the-art benchmarks are performed on this machine. The devices used are listed below. RPI2, Raspberry Pi 2 V1.1, BCM2836, ARM Cortex-A7, 900 MHz, 32-bit quad-core, 1 GB RAM. RP3, Raspberry Pi 3 Model B, BCM2837, ARM Cortex-A53, 1.2 GHz 64-bit quad-core, 1 GB RAM. RP4, Raspberry Pi 4 Model B, BCM2711, ARM Cortex-A72, 1.5 GHz 64-bit quad-core, 4 GB RAM. For the first set of tests, to compare the different devices under equal conditions, all devices were installed with identical versions of the operating system, Ubuntu Server 20.04 LTS, and the OpenSSL branch with PQ algorithms, OpenSSL 1.1.1 U, May 30, 2023, Open Quantum Safe 2023.07. In this case, using an older version of OpenSSL is less critical than ensuring that all tests are performed with the same operating system and libraries without porting between architectures. Although the latest versions of OQS library are based on OpenSSL 3.x, the tests carried out show no apparent performance differences with respect to the version used in this work. Using the same OS version and libraries on all devices without cross-compilations provides a uniform platform for identifying device-to-device variations. For the second part of the experiments, based on the CA application, interoperability between systems is a fundamental element. Therefore, we have chosen to use the latest stable versions of OpenSSL and the OQS provider. OpenSSL run list providers. Providers. Default. Name, OpenSSL default provider. Version, 3.0.15. Status, active. OQS provider. Name, OpenSSL OQS provider. Version, 0.8.1-. Status, active. In contrast to the execution times of each test, which are measured by each operating system, the energy consumption variations require monitoring by an external device. Although there are commercial devices to measure energy consumption, in this case, we decided to use a well-known current sensor such as INA219 to manage its reading periods more accurately. As shown in Figure 10, we mounted the sensor on a protoboard connected with an ESP32, which reads the sensor measurements and writes them through the serial port. This circuit is powered by an external 15-watt, 5-volt DC power supply and supplies power to the test devices through a USB port. Device energy consumption reference values. IoT devices are very heterogeneous, both in terms of their hardware performance and the functionalities they perform. As the framework we propose, each device's typical energy consumption must be characterized performing recurring function. Evaluate the feasibility of a new algorithm or process. Internet of Things 34, 2025, 10. Cruz-Piris et al. 1. The IANA219 high-side DC current sensor breakout is connected to ESP32 on the breadboard below. The device is powered 15W power supply, left connector, displays the instantaneous reading on an OLED display, and returns the readings over the serial T connector. This device also powers the Raspberry Pi. Table 1. Mean values and standard deviations in MW for each device and test performed. Devices: base, network, disk I/O. Mean, STD. Mean, STD, mean, STD. RPI 2, 1476.93, 47.93, 1962.02, 183.79, 1770.98, 135.49, RPI 3, 1632.64, 31.04, 2504.27, 312.27, 2091.74, 294.93, RPI 4, 2149.65, 73.09, 3670.50, 375.53, 3037.71, 392.96. Base consumption. The device is powered for the first time. When the measurement stabilizes after power on without running any programs in addition to the basic operating system tasks, the mean value of the default power consumption is calculated. Network-intensive operations. Measurement is carried out while downloading a file using the Ethernet interface. Disk I/O. Measurement occurs during an intensive disk read-write operation. The size of the memory block used for read and write operations to disk and the files sent over the network is the same for. As shown in Figs 2A, 2B, and 2C, each generation of Raspberry Pi requires more instant power than the previous one, performing the tasks in significantly less time. Table 1 shows the mean and standard deviation values in MW of the instantaneous power measurement recorded by the sensor captured, each device and test performed. We also considered more powerful devices, such as the Raspberry Pi 5, but the results obtained, with mean power consumption above 5000 W, led us to discard it as it can no longer be considered a low-power device. Tests performed. The first set of tests executed by the framework involves running the following 3 scripts. Internet of Things 34, 2025. Cruz-Piris et al. 2. Energy consumption, MW, of the tested devices, boot, network, and disk access. The blue lines represent instantaneous consumption. The green zones indicate periods of stable energy consumption. 2. Gen keys. Uses different OpenSSL commands, gen RSA, dhparam, ecparam, gen pk, to generate a private key of each algorithm. 3. Gen certs. Uses OpenSSL CA command to sign certificate requests by emulating the behavior of a minimal CA application. After obtaining the performance and energy consumption values of the tested devices, the second phase of the framework indicates the behavior of a certification authority application. Beyond the tests available in the distribution of OpenSSL, we have implemented our own framework to experiment with PQ algorithms. The framework is available at the data repository, too. This was motivated by the need to select which PQ algorithm assay, since in the last 3 years the support in LiboQS has extended to many different algorithms. At the same time, different algorithms have been supported in the OpenSSL port, including the changes in the OpenSSL LiboQS provider, which, since OpenSSL v3, introduces a new architectural approach. The algorithms with public keys larger than the maximum extension defined TLS 1.3 RFC 8446 for opaque key exchange 1 to 2 to the 16-1 were left out of the scripts, i.e. the classic Mixel. Rhythms. Besides, we follow a client-server approach using the S.client and S.server to measure the performance and energy consumption separately. The framework also offers the automatic creation of self-signed CAs with the different PQ-DSA and issue certificates to certs and clients to cover all the possibilities, including hybrid certificates. For instance, we can specify a CA with a root certificate issuing a hybrid signature MLDSA 6519 combining material from PQC MLDSA 55 and EC ED259, as shown below. Certificate. Data. Version 3.0x2. Signature algorithm. MLDSA 6519. Issuer. CES ST Madrid. O Trusted Developers. CN Cert Authority. Validity. Internet of Things 34, 2025. Cruz-Piris et al. Public Key Algorithm. MLDSA 65_ed 2515, MLDSA 65_ed 2515 Composite Public Key. MLDSA Key Material 0B, C5, CA, 81, B7, 33, 5F, E4, D0, 90, 4E, B3, 40, E9, N dot, 4F, FE, ED2559 Key Material, EB, 26, CB, 91, BF, 37, D8, BO, 10, A6, DA, 50, 33, F6, 0C, 03, ED-D, F2, 33, SE, A5, F4, 2A, 95, 67, 3D, 36, X509V3 extensions. Signature algorithm, MLDSA 65_ed 2515. Signature value, 3082 OD35 03 82 OCE OOCF 11 AD56 BF 2A F3 09 N dot OF. Our chem tests are configured with a root RSA CA certificate trusted by the client and server. We leave for future work to etch a root CA using different PQ-DSAs exhaustively, since we did not want to mix both effects in the present work. Effects of power monitor in tests. The INA219 sensor, as shown in Fig 1, is controlled by an ESP32 board. To automate the process and ensure the reproducibility of the measurements, 2 digital lines have been connected between the different Raspberries Pi and the ESP3 board. At the start of each bash script, One of the digital ports on the Raspberry Pi is enabled, high level, and the ESP3 board starts the measurement process. The other digital line indicates the exact time measure where a cryptographic operation is carried out. At the beginning of a command set that executes the bash script to perform a cryptographic process, this second port is enabled, high level. When the process is completed, the port is disabled again, low level. Because of that, the energy measurements taken by the INA219 sensor are directly associated with each test. These measurements are transmitted through the serial port of the ESP3 board and collected on an external computer. The time required for each device to change the value of a digital port is not zero. Because of this, the effect of the energy consumption measurement system has been studied to establish whether it affects the execution time of the tests. To evaluate the impact of the measurement system, an experiment with the following characteristics was carried out. The test suite has focused on the family of elliptic curve-based algorithms P256, P384, P521, X448, X2559 for chem. The test was repeated for each device by feeding it with its original power supply and using the measurement system. In the case of the chems test, only the client was run on the devices to isolate the test, with the server functions implemented on an external computer. This test aims to establish the delay introduced by turning a port on and off with commands from the bash script. The difference in execution rates was 64.85 milliseconds, 8.90 milliseconds, and 9.03 milliseconds for Raspberry Pi 2, 3, and 4 respectively. Although all values are low and remain stable over time, the GPIO driver used by Raspberry Pi 2 is significantly slower than used by Raspberry Pi 3 and Raspberry Pi 4, which is reflected in the timing. Anyway, these results allow us to conclude that performing the experiments with the power consumption measurement system will not alter the execution times obtained. Results and discussion. This article has a main driver, the advent of quantum computers, in terms of the so-called store now and decrypt later, SNDL. This threat is motivating the implementation of new security measures to prevent the potential leakage of confidential communication information in the future. In the past, we already implemented perfect forward secrecy to resist powerful adversaries which could break our secret keys. In this work, we experiment with PQ, post-quantum cryptography, and return standards in IoT as a prevention measure for SNDL. All numerical results for each test are collected in the repository. 2. Chem Comparative. This set of scripts was designed to test and compare the overhead of different chems when executed on the test devices. The experimentation comprised 1. 5 classical elliptic curve algorithms. Internet of Things 34, 2025, 100. Cruz-Piris et al. 3. Using chem in the TLS handshake agreement. Comparison of using classic, PQ, and hybrid groups. Time and energy are shown rhythmic scale. Justification of using these algorithms is that they were the ones supported by libOQS branch of OpenSSL, being OpenSSL M most popular security libraries. In all the cases, the server used a 2048-bit public key RSA in a certificate issued by and authorized by the client. Figure 3 shows all the values obtained for this set of tests. The cells corresponding to the TLS handshake using Bykel for RASBand are empty. This is because the implementation used makes calls to 64-bit microinstructions, and this device's processor has x86 ARM architecture. Although it is possible to port between libraries, we think this could have affected their performance among the measured measures. It is interesting noting the very little difference between a PQ pure scheme versus a hybrid version. For instance, in Kyber 512_Kyber 512, the difference is between 1.7% and 6.76% respect the time duration, and between 7.13% and 0.77% respect energy consumption. In Kyber 1024 versus P521_Kyber 1024, the percentage differences are 0.26%, 3.8%, and 0.31%, 4.27% respect time and energy consumption respectively. This fact shows that the use of hybrid chems does not impose a large difference even for IIoT. Introducing this extra security in the handshake is affordable in terms of battery consumption. Thus, we strongly recommend hybrid chems in IIoT and other environments where battery is one more of the design requirements. DSA key generation. Although key generation may be a task that is not performed on end devices, this test allows us to evaluate the performance of algorithms on resource-constrained devices. Table 2 shows the mean times and standard deviations obtained from repeating each private key generation process 20 times.
Cruz-Piris et al. E2, nm time used by each device to complete the key generation operation. Leak key system. Time ms, rp2, rp3, rp4. Mean, std. Mean, std. Mean, std. 2048, 3.67483, 1.630.92, 617.57, 385.02, 295.52, 19, 3072, 11.949.02, 5409.19, 2255.20, 1791.39, 1025.36, 75, 1024, 56,455.86, 54,546.43, 6,840.95, 5,195.48, 4,286.83, 400. ECP 224R1, 42.54, 0.86, 25.73, 1.06, 14.99. ECP 384R1, 61.61, 1.34, 31.27, 1.05. XP 521R1, 100.61, 1.01, 42.14, 1.09, 26.56. Prime 256 V1, 36.41, 2.99, 20.0, 1.76, 14.25. Brainpool P512R1, 71.10, 1.53, 36.15, 0.65, 22.73. Lithium 2, 41.67, 7.95, 26.63, 10.69, 14.61. Lithium 3, 43.50, 1.19, 23.82, 0.62, 14.63. Lithium 5, 49.31, 1.45, 24.88, 0.73, 15.02. Bion 512, 274.43, 126.10, 68.23, 11.67, 34.13. Bion 1024, 714.0, 250.86, 133.51, 31.03, 70.30. 1. 4. Mean energy mj consumed by each device to complete the key generation operation. Due to the high power consumption of some algems, the graph is shown using a logarithmic scale. Signatures comparative. We have performed some tests to compare the time consumption of classic digital signatures with PQ1s. Our experiment ate up different certificate authorities CAs using different digital signature algorithms, and have each of the CA signing certificate for each of the considered algorithms, creating in a first step the keys, then using the command OpenSLCA. Fig 5 presents data from one of these experiments, comparing the values obtained for MLDA65/ED2559 with a set of PQC rigid algorithms. In addition to the 3 devices used in this work, the data also includes results from the Raspberry Pi 5. Chem versus DSA. In Table 3, you can find the comparison of DSA versus Chem attending to performance in microseconds in the RPI-3. There is a notable difference favoring Chem. This is the important fact that motivated studies like 8,40. Nevertheless, the new candidate signature algorithms have come to diminish. Attending to their performance, the best promising candidates are OV and Hawk. The main drawback of OV is the size of the public key, making it a good choice for applications that require small signatures less than 100 bytes, fast verification, and offline transmission of the key. Also, Hawk has been recently reported to have much smaller public keys, around 1043 bytes, and signature sizes, though the NIST 9 still warns the security arguments for Hawk have Internet of Things 34, 2025, 110,
Cruz-Piris et al. 5. Total time in seconds required to complete the entire process of a CA application using keys based on PQC and hybrid algorithm. E3. DARD, draft, and latest candidates algorithms, DSA vs Chem. All times are in microseconds in the RPI-3. A. Gen key. Sign. Verify. Chem. Gen PK. NCAPS. D. WK-512. 25770. 732. 373. ML Chem-512. 89 100. WK1024, 109 430, 1585, 1574, ML Chem-768, 136 147, IP 13 442, 278 236, ML Chem-1024, 193 209, IS 29 274, 603 221, SNT RUP 761, 25 1850, 955, II 113 172, 2164, 973, HQC 128, 12 432, 24 843, V 562 814 6091 204, HQC 192, 37 951, 75 861, 1, Con 512, 43 624, 1336, 2, Con 1024, 116 945, 2726 453, DSA 44, 575 3269 666, DSA 65, 939 4905 1034, DSA 87, 1474 5911 1629, SS 128, 73 3336 2015, SS 192, 130 7266 4584, SS 256, 205 12755 7881, HINCS plus 128, 10 874 254 362 15018, HINCS 192, 15 767 407 616 22148, HINCS 256, 62 795 1269 075, 33208, YO 1 261 389 2842, YO 2 213 761-1685. Yo. 3. 7201-11-188-788. Yo. 5. 17-364-27-230, 18,490. Uments, and underlying assumptions for Hawk more deeply, in order to enable further comparison with NIST's current signature. Standards, discussion, and recommendations. Based on the data obtained, we can confirm that the execution time and energy consumption required to implement an IoT/IIoT-M based on post-quantum cryptography are similar to, or even lower than, those of traditional cryptographic algorithms. All tests demonstrated the correct operation of the main PQC algorithms on the tested devices, even on the oldest ones. Although RPI-2 was able to complete all the tests, its execution times were, in some cases, up to 10 times longer than those of the others. In this paper, we do not assess the security level of each algorithm. There is still significant work ahead for the community to extensively test this field, correct potential implementation issues, and explore techniques that can solve the underlying mathematical problems. As a result of this work, we provide a comprehensive test datasheet, a framework that facilitates the reproducibility of the results on other devices, and an energy consumption measurement system that supports the selection and implementation of algorithms in IoT, IIoT environments. Regarding the chem evaluation, our first and most important observation is that most PK chems are competitive in time. Internet of Things 34, 2025. 10. With Piris et al. Ions of Kyber chems, there is only less than a 6% difference of mean times in RP2 and less than 2% in RP3 and RP4. Of course, penalty increases with the security of the selected chem. Our second observation is similar to what we already derived in section 3.4. As the computing power of the device executes chem increases, so does the power consumption, but the time to compute the chem decreases. Since E equals PT, in the end, algorithms requiring less computation time are also the more energy efficient. Note that only in the logarithmic scale the x86-64 appear, and that they follow the same trend as of the algorithms in the other devices. The introduction of the different variation of Frodo parameters with the accept Frodo 640AS took between 4 to 14 times more than the rest of the alternatives. Frodo variants are not competitive for chem agreements, and this is especially relevant when the computing power of the device is limited, i.e. for IIoT. When it comes to Kyber-based chems, the selection of security parameters does not affect the execution time in the lib implementation in any of the tested architectures, i.e., the execution time is very close for a given architecture, though it decreases with the computation power of the architecture. The only difference is introduced by the larger size of public/secret keys and hexatext. As shown in recent studies like 41, P256 shows much better execution times than P384 and P512. This behavior extends to hybrid schemes, i.e., combining a PQ with an elliptic curve. Specifically, the total handshake time of Kyber variants is similar to the handshake time of the corresponding elliptic curve. All hybrid schemes involving one curve and one post-quantum dependent of the curve. When we explore the performance of the different chem agreements per se, not using them inside handshakes as we show in Fig 6, we see that key generation time makes the difference. Even when we consider the classic Mikkel's Rijjalum algorithms, they are competitive in NCAPS decaps operations. Nevertheless, if we take into account the chem agreements inside TLS handshakes and we group the time and consumption family of algorithms, we appreciate a much different situation. The time spent to perform the TLS handshakes in RP2 using PQ or hybrid PQ algorithms is much larger than classic ones. InSINA 1219 device measurements ensures that RP2 is working at its maximum peak rate with all the algorithms. That is why there appears no difference between the algorithms when executed at the RP2, in contrast with the subtle differences shown by RP3-4 between algorithms. Finally, taking into account that energy is the product of the power by the time spent by each algorithm, the energy consumption in each device for the different families of algorithms is very similar to the time spent. The results of the signature evaluation confirm something we knew beforehand, that the time to sign a certificate with a Gitter algorithm is only impacted by the size of the certificate, something which is directly related to the size of the public key of the certificate. 1. CAM and signatures in IoT. IoT characteristics may favor different schemes which are not so interesting for other scenarios. For instance, normal TLS, frequently HTTPS, rely on signature algorithms to provide authentication to the server side. The server, which authenticated using a GID-19 certificate, demonstrates its authenticity signing with the corresponding private key. Nevertheless, PQ digital signatures behave worse than CAM agreements in terms of time and consumption. In fact, the good performance of some PQ chems has been studied, 40, to propose a new version of TLS which does not use signatures for TLS authentication but key encapsulation agreements, ChemTLS. In ChemTLS, instead of using the public key of the certificate signer, a double chem agreement is used to derive a common symmetric authentication key. The authentication key is used to provide message authentication codes. This situation is balanced when we take into account the latest signature algorithm proposed as shown in Section 4.4 and in Table 3. The drawback of chems is the size of the PQ public keys that have to be exchanged to the other side, and that for very large chems, like Frodo and others, can have a deterrent effect when combined with high losses networks conditions, like studied in 2.8. To address this problem, they propose an enhanced version of ChemTLS with pre-distributed public keys, ChemTLS PSK 8. They show, when the security requirements impose the use of PQC, ChemTLS PSK outperforms TLS with PQ signature both in bandwidth computation. Additionally, they show that when public keys are pre-distributed, some PQCs like Classic McEllies and RAIN are viable. This is something that can work with the IoT requirements, where connections can be long-lived and the number of end users involved in interactions are orders of magnitudes less than in usual Internet client-server scenarios. Besides, so huge public keys will require either a pre-distribution scheme or a new TLS version due to the actual size limitation of the key share field. In Fig 6, we are experimenting the same effects as noted by 8, which claimed that if public keys are pre-distributed, the performance of the different chems is significantly similar, and that even classic McEllies behave better than others. In other words, pre-distribution is the only way to overcome the key size limitation of TLS as explained in 3.3. In this section, we have seen the experimentation with PQC, notably in the area of TLS handshakes and digital signatures. There have been studies on plain chem agreements not being part of TLS handshakes and even studies consumption of PQC algorithms on limited devices. But we have identified the need of further experimentation using limited devices in IoT. Nevertheless, we have been able to propose a new methodology for including PQ algorithms in IoT. Conclusions. In this work, we present a framework that includes a set of tests for evaluating the performance and energy consumption of Internet of Things 34-2025. With Piris et al., Fig 6, Chem Agreement in x86_64, comparison of public key generation and caps and decaps time. When different devices, the same operating systems and libraries have been used. The proposed framework can be easily adapted to other types of environments. We have motivated the works on PQC, which comes from the actual threat store now and decrypt later, and we have flyly presented the new PQC algorithms. Then we have built a testbed for measuring and comparing classic cryptography in an IIoT environment, using 3 models of ARM-based limited devices and a device to measure the energy consumption. We have set up our own set of tests, we have characterized the 3 devices and their consumption in different situations. We have tested the tests and obtained some results. All of them will be made public when the article is published to ensure the results may be independently repeated. Finally, we have discussed the results and we have achieved some important conclusions that we recommend. First, most PQ chems are competitive in time and energy consumption with classic curves and are ready to be used in most IIoT scenarios. Internet of Things 34, 2025, 10. Cruz-Piris et al. Third, regarding the devices used for the tests, RP2 works always at its maximum peak rate with all the algorithms, so time required for the computation is an accurate indicative of the energy expended. In the RP3 and RP4 models, there can observed some variations in the cores, which make the consumption vary. Even more, the more recent device's consumption, National Institute of Standards and Technology, Module Lattice-Based Digital Signature Standard 2024, http://dx.doi/10.602.8/nist.fips.204, https://csrc.nist.gov//pubs/FIPS/pubs/FIPS/204/final. National Institute of Standards and Technology, Stateless Hash-Based Digital Signature Standard, 2024, http://dx.doi/10.602.8/nist.fips.205, https://csrc.nist.gov/pubs/FIPS.205, final. M. Schneider, N. Gamma, P. Baumann, L. Nobach, SVP Challenge, Hall of Fame, https://www.latticechallenge.org/svpchallenge/halloffame.php. AX, 27 March 2025. P. Schwab, D. Stabila, T. Wiggers, More Efficient Post-Quantum Chem TLS with Pre-Distributed Public Keys, in E. Bertino, H. Schallman, M. Wadner, E. Computer Security, ESOR IRSC 2021, Springer International Publishing, CHAM, 2021, pp. 3-22. G. Alajic, M. Bross, P. Chiadux, D. Cooper, Q. Dang, T. Dang, J. Kelsey, J. Lichtinger, Yi Liu, C. Miller, D. Moody, R. Peralta, R. Perlane, Internet of Things 34, 2025, 10.
Cruz-Piris et al., M. Vidakovich, K. Milicevic, Performance and Applicability of Post-Quantum Digital Signature Algorithms in Resource-Constrained Environments, Algori, 16, et al., 2023, http://doi.org/A16110518, URL https://www.mdpi.com/1999-4893 1-16/11/518, X Li, J Lu, D Liu, A Li, S Yang, T Huang, a high-speed post-quantum crypto processor for crystals dilithium, IEEE Trans Circuits Systems 2X, Briefs 2023. A. C. Mert, D. Jacquemin, A. Das, D. Matthews, S. Ghosh, S. Roy, et al., a unified crypto processor for lattice-based signature and key exchange, Trans Compute 2022. D. Campbell, C. Rafferty, A. Khalid, M. O'Neill, Acceleration of Post-Quantum Digital Signature Scheme Crystals Dilithium on Reconfigurable Hardware, in 2022 32nd International Conference on Field Programmable Logic and Applications, FPL IEEE 2022 pp 462-463. T. X. Pum, P. Duong-Nok, H. Lee, an efficient unified polynomial arithmetic unit for crystals dilithium, IEEE Trans Circuits Systems I Regular PAP. T. Wang, C. Chang, P. Cao, D. Gu, efficient implementation of dilithium signature scheme on FPGA SoC platform, IEEE Trans Very Large Scale SIST VLS SIST 39 2022 1158 1171. N. Pratiwi, M. R. Fermancia, M. F. Ezerman, implementing crystals Kyber and dilithium in Intel SGX secure enclaves, in 2023 IEEE International Conference on Cryptography, Informatics, and Cybersecurity, ICO 6, IEEE 2023 pp 77-81. Y. Yao, H. Kwang, Yai Sun, Z. Yang, C. Chen, J. Meng, J. Han, enhancing RISC-V vector extension for efficient application of post-quantum cryptography, in 2023 IEEE 34th International Conference on Application-Specific Systems, Architectures, and Processors, ASAP, IEEE 2023 pp 10-17. A. Ikata, A. C. Mert, M. Imran, S. Pagliarini, S. Roy, Kali, a crystal for post-quantum security using Kyber and dilithium, IEEE Trans Circuits Systems I Regular PAP, 72 2022 747-758. T. Pornin, New Efficient Constant Time Implementations of Falcon, 2019, http://eprint.iacr.org/2019-893. Cryptology ePrint Archive, Paper 2019/8. D. O. Greconici, M. J. Canwisher, A. Sprankles, Compact Dilithium Implementations on Cortex-M3 and Cortex-M4, IACR Trans Cryptography Hardware MPAR, SIST, 2021. 1-24. D. J. Bernstein, D. Hopwood, A. Hilsing, T. Lang, R. Niederhagen, L. Papakristodolu, M. Schneider, P. Schwabe, Z. Wilcox O'Hearn, Spinkus, Practical Stateless Hash-Based Signatures in Annual International Conference on the Theory and Applications of Cryptographic Techniques, Springer, 2015, pp. 368-397. M. J. Conwisher, R. Petri, J. Reineveld, P. Schwabe, K. Stoffelen, PQM4, Post-Quantum Crypto Library for the ARM Cortex-M4. https://github.com/mpq.4. C.A. Roma, C.E.A. Tai, M.A. Hassan, Energy Efficiency Analysis of Post-Quantum Cryptographic Algorithms, IEEE Access 9, 2021, 71295 to 71317. Y. Dai, Y. Sun, J. Tian, Z. Wang, High Throughput Hardware Implementation for Haraka in Spincus Plus, in 2023 24th International Symposium on Quantum Electronic Design, ISQD IEEE, 2023, pp. 1-6. M. Kudino, H. Hilsing, E. Ronan, E. Yogev, SPHINCS, C. Compressing Spincus Plus with Almost No Cost. Cryptology ePrint Archive, Paper 2022. M. Sim, S. Yom, G. Sung, Y. Yang, W. Kim, H. Seo, KXMS and KSPHINCS. Enhancing Security in Next-Generation Mobile Communication and Inter-RIS Systems with Hash-Based Signatures using Korean Cryptography Algorithms. Sensors 23 17 2023 7558. R. Mondev, E. B. Kavun, Performance Comparison of Post-Quantum Signature Algorithms through an Android Email Application Plugin, in 2023 International Conference on Omni-Layer Intelligence Systems, COINS, IEEE, 2023, pp. 1-18924. M. Ravi, S. Wuthier, P. Chandramouli, Y. Balitsky, X. Zhou, S. Y. Chang, Security Comparisons and Performance Analyses of Post-Quantum Signature Algorithms in International Conference on Applied Cryptography and Network Security, Springer, 2021, pp. 424-447. C. Pakan, D. Stebola, G.